All right. Well, good morning, good afternoon, good evening, good middle of the night, whatever it is for everybody. Thanks for showing up. I'm going to talk about some experiments that were done by Mauro Passarella. So I'm giving him top billing here because this is all from his PhD thesis. Mauro defended his thesis in November 5th last year successfully and has received his PhD. And he will be taking a postdoc position at the University of Bergen in Norway. So these experiments were, one of the main aims of this study was try to do seawater basalt interactions at high temperature in a continuous flow apparatus, which is extremely difficult. So the idea was, how do we do this? Well, first we have to start the thing at different levels of complexity. So obviously we start with an unaltered basalt. This basalt came from Reykjanes Peninsula in Iceland. It's unaltered. And we tried 3 different fluids, so increasingly complex. So we started with distilled water, which is like a control to see what the rock does. Then we chose a geothermal brine, which comes from a New Zealand power plant. And then natural seawater, which came from the New Zealand National Aquarium in Napier. The conditions, now Mauro did subcritical and supercritical conditions, but we were looking at high pressures because we were looking at mid-ocean ridge type environments. So the pressures are much higher than what supercritical geothermal might be at. So here you see the blocks of basalt. They're crushed, cleaned, and sieved to obtain different size fractions. And here's a EDS map of the polished grain, and it's mostly composed of bitonite plagioclase plus clinopyroxene with lesser amounts of olivine and iron oxides. There's about 0.5% glass in the rock. So some interesting and important parameters to consider. Now, Peter showed you the apparatus already, so I won't go into too much detail, but we're using continuous flow hydrothermal apparatus. The flow rate in the experiments was 1 mil per hour. There's nothing magic about this flow rate. It's just so we get enough sample every day to analyze it. It's basically the minimum we need to get enough fluid out every day. We sample every day. The rock, as I said, basalt grains. The total mass of rock in the experiments is averaged about 25 grams. And if you calculate a geometric surface area based on the average grain size, you get 1.12 meters squared, which is essentially a surface that's 34 centimeters by 34 centimeters. So that's what your surface area is looking like. Measured porosities were between 45 and 55%. So porosity about 50%. And interestingly, if you calculate the porosity based on spheres of that average grain size, you get 56% porosity. The fluid volume, so the instantaneous fluid volume at any moment is 10 mils in the pressure vessel. And so that means the average residence time of the fluid is 10 hours. Each experiment lasts at different lengths, and you know, if you've done experiments, the end of the experiment is usually when the thing breaks down. So the volumes varied from 700 to 1500 milliliters. Now, what's interesting is if you calculate a water layer thickness, an average water layer thickness over that surface area, you get 90 microns as the average water thickness layer. So it shows that there's a very thin layer on average of water coating the rock. If you include a surface roughness parameter, that one number drops even further down. So like if surface roughness of, say, a parameter of 5, that drops down to 16 or 18 microns of water. So now I'm going to focus on the seawater, but I'll just briefly show a couple of slides about the results from the distilled water and the brine experiments. So you can see selected chemistry there on the left, and you see different types of behavior. So again, on the bottom is time in hours, so this is 1,000 hours, and millimole on the vertical axis. And you see different behaviors. Okay, so the different colors here, ignore the 2 red ones at the end. The yellow square is the input composition, so this is just still water, so it's basically 0. And these 5 points are pure water flowing at room temperature for a week. And then this temperature shift occurs at about 150 hours. And you see a rapid increase in silica concentration well above quartz solubility, and then a rapid decrease again after about 15 days. And this is the glass dissolving from the basalt. So it takes about 2 weeks for the glass to dissolve completely from the basalt. So the different types of behavior that you see, because we're interpreting the flow regime in the column as plug flow, that means there's not a lot of vertical mixing in the column. Because if there was a lot of vertical mixing, all the chemistry would be smeared out. So there's clear alteration fronts moving through the column. This one here with the sharp drop of silica is the actual dissolution of glass. So there's a very sharp point in the column where glass is gone. So over a few days, it just disappears. Then when you get plateaus like this, that means that it's either steady state concentration or a equilibrium concentration controlled by the rocks, the minerals in the rock. Now, when you look at something like potassium, it has a number of different shapes going on here. It's first increases, decreases, and increases, and then decreases again. These are different alteration mineral switching back and forth. And when they're curved or smeared out, it means that alteration front is smeared. It's spread out over a wider area in the column. But eventually, the potassium, it drops down to a steady state value of down here. Now, just going back to the glass, we know this is the silica is coming from the glass because there's no quartz in the rock, and the solubilities are very high. This solubility, however, is rate controlled, because if you slow down, the silica will actually go up. So quartz does not precipitate. It's not precipitation of quartz has not been induced in these experiments. Other thing that happens when the glass dissolves, it releases what's dissolved in the glass. So, for example, there's sulfur dioxide probably dissolved in the glass. It's being released, forming sulfate. There's chloride in the glass. It's being released. We also see the release of H2S because the glass contains immiscible iron sulfide blebs, and they dissolve, so you get an increase in iron and hydrogen sulfide as the glass dissolves. Now, when you look at the rock, without going into a lot of detail, at the entry point, the rock has been converted to a calc-silicate-like skarn-like assemblage, formed of grossular garnet, wollastonite, anorthite, and chlorite. And you can see these lovely dodecahedra of grossular. You can actually see them with your eye, and they're brown like grossular typically is. And you have nice, neat radiating needles of wollastonite. And at the top of the column, however, there's very little alteration. And the only thing we see is the replacement of olivine by seladonite. And this is known in nature. And it's always been said that this is caused by seawater. But what we're actually finding here is that the release of the potassium from the glass is inducing seladonite precipitation, replacement of olivine. We look at the basalt geothermal brine experiment. We get the same kind of plateau with silica, and notice that it's, again, about the same concentration, but note the input concentration now is much higher because this is a geothermal brine. Again, this is because the flow rate, it's dissolving only up to a certain amount. And then it drops out, so the glass disappears, and we see again an increase in potassium because the glass is dissolving. But this time the sulfate actually decreases because the brine is acid dosed. So in the plant, so it has a very high sulfate concentration. So as a result, when it goes through the rock, sulfate's actually decreasing. Again, we see a release of this time I showed you hydrogen sulfide because the glass is dissolving, releasing the iron sulfide, or dissolving the iron sulfide. When we look at the rock, we see something very different. At the bottom of the column, the rock is converted to an assemblage of anhydrite and biotite. So this is potassic alteration of the basalt. And that's because of the very high potassium concentration in the brine. And that replaces all the silicate minerals. And the release of calcium from the plagioclase and the pyroxene, of course, causes the saturation of anhydrite. And this precipitates anhydrite in the rock. However, at the top, we get an unusual precipitate, which one wouldn't expect, which is smectite. And all you geothermometry people out there are going to jump up and down and say, oh, you can't get smectite at 400 degrees. Well, you can actually, and it's been shown experimentally. You can get it up to 450 degrees. It's probably metastable because you wouldn't expect to see it in nature. You might expect to see something like chlorite instead. Now, the real problem is, how do you do this with seawater? The problem with seawater is it contains lots and lots of calcium, magnesium, and sulfate. And what happens is when you heat seawater, these minerals saturate because they have what's called retrograde solubility. So you see, as the seawater, this is a Geochemist workbench model. The database only goes to 300, but you'll get the point. This is the saturation index of the minerals with increasing temperature. So what you see is that you heat seawater, brucite actually saturates at about 70 degrees. And then anhydrite saturates at 108 degrees. And then this magnesium hydroxysulfate mineral saturates at about 180 degrees. Now remember this was identified by Bischoff and Seyfried in 1978 in their experiments progressively heating up seawater. And they identified it by SEM, I believe, and but there was no known mineral at the time. Well, in 1986, Heyman and Kostner published a paper on the mineral caminite. And caminite is a mineral that precipitates in hydrothermal chimneys that was found in the East Pacific Rise. And why it's so rare is when the chimneys cool, that mineral redissolves in water again. So it's very rare in nature. But it's the same mineral that was found in the experiments of Bischoff and Seyfried in 1978. So that's the problem. Now, what's the point of this? Well, the thing is, remember, we have small gauge titanium tubing, right? And as that tubing passes down the pressure vessel, it heats up, and you can see what's going to happen. There's hundreds of ppms of these solutes in seawater, and so you would block up those titanium tubes within a few hours, or maybe a few days even. And so it's really difficult to use flowing seawater in a progressively heating environment. So how do we get around this? I'm sure there's more than one way, but this is the way we did it. We designed a titanium pressure vessel, which is very similar to the one used for containing the rock. It has a length of 56 centimeters and an internal volume of 70 mils. And what we do is we place that pressure vessel inside the oven, such that about 20 centimeters of it is sticking out the top of the oven, and we have a fan blowing on it to keep it cold. The bottom of the pressure vessel is in the bottom of the oven, and it could only get to a maximum temperature of 377 degrees because of the large heat conduction up the column. This column contains 2 millimeter zirconium oxide beads, so we have a huge temperature gradient from 40 to 377 degrees down the column, and the beads are just to create surface area. So if we look at some of the chemistry coming out, the yellow squares again are the input seawater composition, and note for sulfate it's 22 millimoles. It's up here somewhere. And chloride. This chloride here, you see the mixing. So this is at room temperature with distilled water, and then we switch to seawater and increase the temperature, and you see it's mixing over a few days. Because remember, the column volume is 70 minus the beads. What we see is a large decrease in the concentration of effluent calcium concentration, magnesium concentration, and sulfate concentration. And the precipitates we see, not surprisingly, are anhydrite, caminite, and brucite, which is exactly what the modeling predicts. So that's what's happening with only seawater. Remember, there's no rock involved here. So now we increase the complexity of the experiments. And what we do is we add in series the reactor vessel, what we call a reactor vessel, and that contains the basalt. So now we've got our preheater with a huge temperature gradient. The water's flowing down. This is 377, not 342. The water's flowing down, heating up, and no doubt going through absolutely complex convection cells as it descends. But eventually, it exits the pressure vessel happily and moves into the bottom of the reactor and passes up through the basalt and is collected. And if you look at selected chemistry, we see now that silica is buffered. It's being buffered by the rock assemblage or the mineral assemblage. We see now, instead of a decrease in calcium, there's the input calcium concentration. Remember, we know the composition of this water coming out, so we're assuming that's the composition of the water going in here. So This is the input calcium, and you see there's actually a large increase this time of calcium. Ignore these color points at the end. Magnesium going in is 24.4 millimolar, so it's somewhere up in my ceiling here. And when it comes out, it's gone. It's essentially zero. There's no magnesium coming out. Sulfate going in is 1.2 millimole, and coming out, it's essentially zero as well. So we have preheated seawater exiting the bottom of the column. The retrograde phases have been removed, so now it can pass through the column and the rock without any hindrance. So what do we see? Now, the results are really complicated, and I just don't have time to go through all the details of what mineralogies were found where. But essentially, the main points are the column bottom is completely converted to chlorite. And we have some anhydrite precipitation in the bottom of the column. And again, we find some caminite because of the release of magnesium from the rock. At the top of the column, the rocks are much less altered, and we see again smectite in this case, and also caminite. But when we take the rock out of the column, so what we have here, this is the rock coming out of the column, so the flow directions from left to right. This is the fluid entry point on the left. This is the fluid exit point on the right. Now, I don't know if how many are familiar with water rock interaction experiments, but I've never seen anything like this before. The alteration, first, the way we're doing it, we can see alteration fronts. And secondly, the alteration is incredibly intense. The rock is completely converted to chlorite, halfway up the column. And that switches to a smectite, and then the alteration is very weak at the top of the column. And based on all the SRM, XRD, and XRF results, we see a maximum of anhydrite precipitation actually in the middle of the column, which is very interesting. What does it mean? What's our interpretation? Well, what we see is, first, the glass dissolution occurs very rapidly, and we don't see it in the seawater basalt experiment because the silica is obviously consumed by the chloritization reactions. The Mg input from the seawater causes intense chlorization, which releases calcium, and this initiates anhydrite precipitation in the rock. The maximum uptake of the rock of calcium is 9 grams per 100 grams of rock. You can't uptake any more magnesium. The rock is completely chloritized, and thus the rock cannot produce any more calcium, as plage and CPX are all replaced by chlorite. So without the calcium, the anhydrite undersaturates and redissolves again. The decrease in magnesium activity due to the chlorization causes the switch from chlorite to smectite. And so what we're interpreting is this is an alteration front that proceeds gradually up the column. Chloritization, releasing calcium, anhydrite precipitation, ceasing of chloritization, dissolution of anhydrite precipitation, decrease of magnesium activity, and the switch to smectite stability. The important thing to remember here, this experiment lasted 29 days. So what we're seeing here is intense alteration. So we developed a novel experimental method that allows continuous flow between seawater and rock substrates without the hindrance of the retrograde mineral precipitation. Now, what we saw in the distilled water and brine experiments is that the glass dissolution is within a couple of weeks, and it releases large amounts of silica, chloride, H2S, potassium, sulfate, and also trace elements, which I didn't talk about. Distilled water is very aggressive, and it converts the basalt to a calc-silicate skarn-like assemblage, while the released potassium alters olivine to seladenite at the top of the column. So what the fluid is doing, the water is doing, it eventually removes all the sodium and potassium from the rock, and so you're left with calc-silicate minerals like grossular, wollastonite, anorthite. But it's happening very rapidly. So it's occurring over less than 10 hours the residence time of the fluid. The geothermal brine is much different in that its high concentration of potassium and sulfate leads to rapid conversions to anhydrite, biotite, and eventually seladenite. So in this case, the geothermal brine causes potassic alteration of the basalt. So the progressive heating of seawater leads to the precipitation of hydrate-producing kemenite, removing significant concentration of calcium, magnesium, and sulfate. However, not all of them are released, sorry, not all of them are lost. So there's still some left in the preheated seawater, which has equilibrated with these minerals. So our seawater basalt experiments provide the first examples of continuous flow experiments using natural seawater and basalt near supercritical conditions. And I guess the main take home would be the rates of reactions are extremely fast. And believe it or not, we think it takes less than a few hours for the rock to essentially fix all the magnesium from the rock, from the seawater. And we see the way we're doing this experiment that allows us to look at progressions of alteration through the rock. And what we see is an alteration front defined by the maximum anhydrite precipitation, which coincides with a switch from chlorite to smectite due to rapid drop in magnesium activity. So the main accomplishment of this thesis was to develop this method, and I can see that you could use this to look at seawater rock interactions in other configurations. But I guess also the really important point here is that these high temperatures, these reaction rates are incredibly fast. So thank you very much.
Thanks a lot, Bruce. Yeah, I can hear myself. That was a really, really clear talk. I mean, obviously, we talked about it before. This is quite interesting because you basically reproduce what is observed into a mid-ocean reach when you have a alteration front with the anhydrite of the external part, and then the mineralization. You can see my deposit background here, and then the allothermal alteration that is different. So how will you expand this type of experiments with seawater in the future to try to even more reproduce this natural environment?
Well, we had this question often asked, where are you taking seawater and sticking it at 400 degrees in the reaction zone with a fresh basalt? And no, that's not what happens in nature. But remember, experiments are increasing complexity. We could use the preheater and actually put rock in it, and that would be like the next step to do. We could actually have pelagic sediments, volcaniclastics, dikes, whatever you want, you could put it in the preheater. But of course, Mauro did 8 experiments for his thesis, right? And that was twice what he needed for a PhD, I think. So yeah, there are ways to make this more complex. And remember, I only presented a very, very small amount of the information. We looked at trace elements and geothermometry and a lot of other stuff, a lot of chemistry. 10,000 chemistry and chemical analyses. So you could make them more complicated, yes, but I think for the next step would be, I'm interested in is putting high concentrations of carbon dioxide in the system. That's what I would look at next.
Sorry, I had an issue with my microphone. Thanks a lot, Bruce. There's a question from Christopher Rochelle. Do you see any precipitation in the exit tubes of the flow reactor when the tubes cool down to room temperature would lead to unduly low concentration being measured?
Do I see precipitation in the small gauge titanium tubing? Is that what you're asking?
Yeah, in the small, in the exit tube, do you see some precipitation?
No, because what happens, we've done a lot of experiments, right? And what happens is the water quenches as soon as it exits the pressure vessel, it cools to room temperature, and immediately silica, there's no precipitation. It just completely quenches. And we learned earlier that if you actually heat the tubing coming out, you can get quartz precipitating in the tubing. We actually had a tube block up with quartz crystals, and we grew millimeter-sized quartz crystals in the exit tube.
Thanks. There's also a question from Evelyn Ains, who is asking if you compare the result of the geochemistry with the altered mineral and mineralogy recovered from some of the ODP expedition penetrating the oceanic crust. So which is a natural example.
I have to, Maro's thesis is accessible online. I would have to refer to the thesis because there's a very detailed description of that in the introduction of the thesis and also in the geological interpretations. But yes, they're very similar. One mineral that we never seem to see is epidote. We can get actinolite, chloride everywhere. I mean, the rock is essentially all chloride, but we never see any epidote. Interestingly, from the IDDP well, they had hematite on precipitates, and I didn't go into the detail, but if you look at the rock in the colored changes, it actually turns pink halfway up, and that's hematite. It was identified in the XRD results. So it's very similar, but remember, we're not taking seawater and basalt unaltered and immediately, yeah, that's what we're doing. That's not what's really happening in nature. Nature is more of a progressive thing.
There's also just someone, can you remind us again under what pressure condition these experiments were conducted? And are you considering changing some of this pressure condition?
Yeah, it could be done. We were interested in mid-ocean ridge type water rock interaction, so we took it to the maximum of the machine, which is 500. So the pressures were sort of 488 to 500 range for all of the experiments. Remember, Mauro did it at 350 too, the same experiments, and just for a comparison. So there's actually interesting differences between the two sets of experiments as well.
Yep, so it can be done. There's someone questioning, and I think that's going to be the last one. Someone questioning the formation of a smegmate, obviously at 400 degrees C plus. Do you think is it possible to form smegmate in real supercritical geothermal system?
Very good question. We went through a lot of soul searching because we only had an SEM EDS to identify the minerals. We didn't have a microprobe here to do it. So I think Mauro may have done some as well, but we're basing the interpretation of smegmate obviously on the composition. It looks like it's got saponite, calcium saponite / montmorillonite composition, but also the texture. When you look at it, it's classic smegmate texture, and we get smegmate at lower. Smegmate is really common at low temperature experiments, like experiments at 150 degrees with rock, with greywacke. We get smegmate. It's obvious, the texture. But Bruce Yardley did some experiments. I can't remember what year it was, but a while back, where they were doing water rock interaction batch type, and they had smegmate forming at 450 degrees. So, is it possible to get it? Yes, it's possible to get it. Will it be there? We need some rocks to look at to see if it's there. Technically, I would think it's unlikely because we know from the geothermal systems that it doesn't form or it destabilizes by 200 degrees, right, Isabel? 200 degrees. Yeah, so it shouldn't, and that's why we had a long time trying to figure out what it was. But then in the end, we decided from seeing these earlier experimental results, no, this is smegmate. And we decided on that.
As there is just one question left for you. It's again from Stanley. Can you speak to the net change in volume of the solid? So basically, or hypothetically, but what is the insight that you get into a change in porosity from this experiment?
Well, that's also a good question. Remember, these rocks aren't under any stress. There's no differential stress on these rocks. If you put some kind of differential stress in these rocks, that chloratized zone is going to squash, and it's going to become very impermeable. So yes, that there would be a considerable loss of porosity or permeability, I would think, if those rocks were under differential stress.
Yeah. Thanks a lot, Bruce.